Hi, I'm going to be doing the topic 14, part 2, additional problems now. I so let's take a look at those. So we see here that for problems 1 and 2, we need to find the effective rate corresponding to the given nominal rate. So the first problem, number 1, states that the given nominal rate is 10% compounded semi-annually. So this is a nominal rate, it's a rate per year, and it's going to be compounded semi-annually. Okay, so let's go ahead and figure out how to solve this one. This is going to be using that effective rate formula that was derived in the part 2 video. And this formula is given by the effective rate is 1 plus R over M raised to the M minus 1. So remember, this is when we're compounding semi-annually, we always are going to be making more money than if we were doing simple interest. But as I explained, understanding what that simple interest rate would have needed to be to get us the same amount of interest is a way to allow us to compare different types of structures of rates and conversion periods. So for us, we're here with this, and we know that the rate is 0.1 for 10%. And because it's semi-annual, we know that our M is equal to 2. So our effective rate is just 1 plus 0.1 divided by 2 raised squared minus 1. So let's go ahead and figure that out. So 0.1 divided by 2 plus 1 squared minus 1. So I get that this comes out to 0.1025 or 10.25%. And that makes sense because we know that compound interest is going to do better than simple interest. So this is the simple interest rate that would be needed to give us the same amount of compound interest if we had 10% compounded semi-annually. Okay. Oh, the second question, let's go see what that one was, is going to be the same question, but now we're dealing with 8%. So our rate is going to be, our annual rate is 8%, and it is compounded daily. So compounded daily. All right. So first of all, let me go ahead and put a red box around the answer to number 1 so we don't lose it inside the whiteboard writing. Okay, so for the second problem, we're just going to apply the same formula again. So our effective rate, which is a simple interest rate, is going to be given 1 plus R, which is 0.08, divided by M, compounded daily, remember, means M is 365. I think by now, hopefully you've got this down. All right. And we're going to raise it to the 365. And when we're all said and done, we're going to subtract 1 off of that. Okay, so let's see what we get for doing that. So this is a calculator heavy section. Okay, so let's take 0.08 and we're going to divide that by 365. We're going to add 1 and then we're going to raise it to 365. And when we're all said and done, we subtract 1 off. So I get that this comes out to a little bit more than 8. You should always be a little higher than your rate. Okay, so that's a good check that you've put everything in your calculator correctly, because I get 0.08 0.0833. All right, so that's 8.33%. Okay. All right, let's go on to see what the next question is. All right, in problems 4 and 5, we're going to use logarithms to solve each problem. So let's go ahead and give that a shot. Let's see. So this is going to be, oh wait, I skipped 3. Okay, for the accumulated amount after 6 years, let's get back to 3, sorry, oops, I'm in red. Find the accumulated amount. So we want to find A after 6 years, so T is equal to 6. If 6,500, so that's our principal, 6,500 is invested at, hold on, I gotta move my chair. Okay, is invested at 8%. So 8%, and it's compounded continuously. Okay, so we're talking about continuous compounding. So remember that's our PERT formula from the lecture video. The amount is the principal times E raised to the RT. So for us, that's 6,500 times E raised to the 0.08 times 6. All right, let's give that a shot. Oh, I apologize. I am not on the big screen. Okay, so I just converted everything I read, and then I realized I needed the continuous um, compounding continuous formula, which is the A equals PERT formula. And so I now substituted everything in here, and I'm going to use my calculator to see what I got. So I get 6,500 times, oh, it's not going to let me do it that way. My iPhone calculator says I have to do the exponent first. So I do the 0.08 times 6, and then I hit the little e to the x button, and then I multiply that by 6,500. And I get that this comes out to be 10,504 and 48 cents. Okay. Oops. All right. So now let's go back and look at what the next question is. Now we're going to get to those logarithm ones. All right. So let me erase some of this. Yeah, I got to remember not to use the red. Okay. So the first problem is, how long will it take $5,000 to grow to $6,500 if the investment earns interest at the rate of 12% a year compounded monthly? Okay, so let's go ahead and set this up. We have our principal, which is the 5,000, and we want to know how long it's going to take to grow. So anytime you want to know how long it's going to take something to grow and you're talking about compound interest, you're talking about solving for an exponent of time. We'll see that here in a minute. But the amount that we want to get to is 6,500. And we have a structure to this investment that earns at a rate of 12% per year. So the rate is 0.12, and it's compounded monthly. So we know our M equals 12. Okay, so in this problem, we want to find T. And remember, T doesn't have to be a whole number. So let me get out of here and get to the full board. Okay, so now remember by our compound interest formula that A, oops, that's not a very good A equals P times 1 plus I to the N. Now, whenever we're trying to solve for T, it's a good idea to go ahead and put the t back in. So remember that n equals mt. So for our purposes, n is equal to 12 times t. So what we're going to do is we're going to replace n with 12t. And then the other thing we need is the I, right? So the I is the rate divided by the number of conversion periods. So it's 0.12 divided by 12, which is going to be 0.01. Okay, so we put everything we know in here now, and we have 6,500 is equal to 5,000 times 1 plus 0.01 raised to the 12t. Okay, so that was a 5,000. All right, so let's go ahead and hoping you guys are seeing this okay in here. Okay, so we're going to first divide both sides by 5,000. All right, and on the, let me get another color. I'm not going to go for red anymore. This cancels out on the left, and on the right, on the left we have 6,500 divided by 5,000. So let's just do that. And we get that this is 1.3. So 1.3 equals 1.01 raised to the 12t. All right, so if we wanted to use the conversion to log formula, we would want to take the log with this base. And obviously we don't have that on our calculator. So what we're going to do is we're going to use the natural log. So if I take the natural log of both sides, I'm just going to apply that function to both sides. Okay, so now we have the natural log of 1.3 is equal to the natural log of 1.01 raised to the 12t. And this is where the whole reason we're taking the log is because of the property, the key property that's so helpful with logs is that we can pull the exponent down in front. So we say that this is equal to 12t times the natural log of 1.01. Okay, so natural log of 1.01 is just a number. So we have 12 times ln of 0.01 times a t. So you can just divide out everything that we don't want here and keep just the t. So let's just write this over here as ln of 1.3. Okay, so we can divide out 12 ln of 1.01 from both sides, and we'll be canceling out here, and we have to put it on this side too. 12 times ln of 1.01. Okay, now this is not ln of 1.3 minus some kind of ln of 1.01 raised to the 12th or anything like that. That would be applying the log rules incorrectly. So if the argument inside of the log was a fraction, then we could say it was the log of one minus the log of the other. But a fraction of logs does not get in any way simplified. This just goes right into our calculator because what we're left with on the right-hand side when we did all this, we got rid of everything except the t. So we actually have now t equals, if I can get the pen, t equals, and everything here on the right, ln of 1.3 divided by 12 times ln of 1.01. So let's go ahead and put that in our calculator. So on my calculator, I have to put in the 1.3 first and then hit ln. And then I have to hit divide, and then I have to use my parentheses. And I have to say 1.01 ln times the 12. And then I close my parentheses for my denominator. And then I say equals. So I get that this is 2.01 197. So depending on how I want to average it, I'm just going to go to the one decimal and say it's 2.2 years. So in 2.2 years, I can grow $5,000 up to $6,500 if I have a nominal rate of 12% a year, and it's compounded monthly. Okay, so the answer is 2.2 years. Okay, now let's go see what problem number 5 is. All right, so 5 says, how long will it take an investment of 2,000? So I think we can fit this in here. So we have the investment is 2,000, and to double. So we want to double it. So the amount that we want in the end is 4,000. If it earns an interest of 9% a year, so our rate is 0.09, and that is compounded monthly. So once again, we're going to have the M equals 12. All right, so now let me go back to the whiteboard. I've written everything out for problem 5, and I'm going to go and use my formula and figure out how much time this is going to take. So the one thing that I need, remember, N is MT. So our N is going to be a 12T, just like it was in problem number 4. And our I is going to be 0.09 divided by 12. And 0.09 divided by 12 is 0.0075. Okay, so we're going to put 4,000 is equal to 2,000 times 1 plus 0.0075 raised to the 12t. All right, so if I divide both sides by 2,000, 4,000 divided by 2,000, we already knew that we did this already because we were talking about doubling it. So we're going to end up with 2 equals 1, and I'm going to add the inside 0.0075 raised to the 12t. All right, so now I'm going to do the same thing I did before and take the natural log of both sides. So take the natural log of 2, and that equals a natural log of everything on the right-hand side of that equal sign. And now I apply my my logarithm rules, which lets me pull down the exponent, right? So now I end up, let me clean it up and write it out as ln of 2 is equal to 12t times ln of 1.0075. All right. And now I just have to put this in my calculator. I divide both sides by the 12 and the ln of 1.0075. And so this cancels on the right, and we got to put it on the left. We're going to divide both sides. Okay. So what does that equal to? So that tells me that t is equal to, because remember I have t in here, and everything else I canceled out. So let me go ahead and put that in and see what I get. All right, so I'm going to take 2 on my calculator. Hopefully, like I said, on your calculator, I said this earlier, hopefully you can just plug this in the way we write it, and you can use parentheses. So you want to use, you could do ln of 2 divided by, and then an open parenthesis for your denominator, and multiply it out as 12 times ln of 1.0075. So doing that, whoops. So 1.0075 ln times 12, close the parentheses for the denominator, and I get that this comes out to 7.7 years. So this structure of this investment will double if you in 7.7 years. So that's a good thing to know. All right, so that's question 5. Let's go on to question 6. Okay, so question 6 says find the interest rate needed for an investment of 5,000 to grow to an amount of 6,000 in 3 years if interest is compounded continuously. Okay, so this is not asking about time, it's asking about rate. So if you're out there shopping for rates, you know the best thing you could possibly get is compounded continuously. So if you want this kind of growth, you want to shoot as much as you can for something like that would satisfy what we end up calculating. So let's see, what we know so far for problem 6 is that we start out with a principal of 5,000 and we want an amount when we're done of 6,000. And we want to get there in 3 years. So we say t equals 3. And what we need is to find the rate, find r. And we're talking about looking at comparisons that compound continuously. Okay. So since we said let's talk about compounding continuously, automatically we know we're going to use the PERT formula. So the amount equals the principal times e raised to the RT. Okay. So now we have what we need. The only catch here is that we will know everything that we want here except for r. So we're going to solve for r. So once again, we're solving for something that's in the exponent. Automatically think strategy is you're going to need to take logs. So let's put in what we know. What we know is that we have a 6,000 amount starting with a principal of 5,000 e to the 3, and I'm just going to put the number in front of the variable. That's kind of the common practice. So we'll say 3r. So now we need to solve for this r. So let's divide both sides by 5,000. Okay, so on the left, we're just going to get 6,000 divided by 5,000, or 6 divided by 5, which is 1. Yeah. All right, so this is just 1.2. So we've crossed this out here, and on what's left on the right is e raised to the 3r. Okay, so now we're going to just take the same strategy we've been taking. We have two things equal, so if we take the log of both sides, they're still equal. So it's the natural log of 1.2 equals a natural log of e raised to the 3r, and we're going to take advantage of this property that lets us get that exponent out. Sorry, let me put the equal sign over here and make sure I make it clear that we're pulling that down. So let's just write this as ln of 1.2 is equal to 3r ln of e. Well, ln of e is just 1, so this problem is actually super easy, right? Because this is a disguised form of 1. So we're just left with 3r on the right. So to solve this, we're just going to divide both sides by 3. And we're going to get that r is equal to the natural log of 1.2 divided by 3. So what is that? So I get that this is 0.061 if I round. So 0.061, and so that is 6.1% is the rate, the nominal rate that we'd be shooting for to be able to go from 5,000 to 6,000 in 3 years with continuous compounding. Okay. All right, let's see what problem number 7 is. Okay, we have 2 word problems left. So the first word problem says, this is a rate comparisons. So remember, as soon as I hear rate comparisons, I start thinking, oh, this must be an effective rate, right? Because that's how we compare things. Well, I could be wrong. Let's read it. In the last 5 years, Bendix Mutual Fund grew at the rate of 10.4% a year compounded quarterly. All right, so we're told 5 years. So T equals 5. And it grew at a rate of 10.4% per year. So that's a nominal rate, right? It's an annual rate, but it was compounded quarterly. So our M is going to equal 4 here. Over that same period, Acme Mutual Fund grew at the rate of, so um, so let's just say I'm going to do 1 and 2 for the 2 different funds. So let me say this is the information for Fund 1, and then we have the information for Fund 2. And so for the same period of time, so T is also equal to 5 here, Acme grew at the rate of 10.6% a year. So that rate is 10.6% per year. Again, nominal interest. And this time it's compounded semi-annually. So M equals 2. All right. So the question is, which mutual fund has a better rate of return? So in order to do that, we can't really compare them because we're not told a principal. So you could kind of play the game of doing a principal, but the correct way to answer this problem, and let me stop sharing now that I have all that information. Okay, so the correct way to answer this problem is to figure out the effective rate. Remember, the effective rate is what the rate would be if you were to apply this as a simple interest over those 5 years. So let's go ahead and use that formula. And by the way, this formula, you do not have to have it memorized. It will be provided if you need to use it on the quiz. The formulas that you absolutely do need to know, you need to know the simple interest formula, you need to know the compound interest formula, and you need to know the continuous compound interest formula. So in the formula sheet I gave you, those are the top 3 formulas. You do need to know those. The effective rate of interest formula is a little more convoluted, a little more obscure, and it's something you would probably look up to make sure you got it right. So especially since we have so much coming at us in this section, that I don't want you to have to memorize it. So what is it today? The effective rate formula. Oops. Okay. It's a way to give us what we're looking for, right? So we need, I can't get Miss Pen to write. There we go. 1 plus the rate over the number of conversion periods, and it's going to be raised to the number of conversion periods minus 1. Okay, so for us, that's 1 plus 0.104, right? That's 10.4% converted to a decimal, divided by 4, which is our number of conversion periods, raised to the 4 minus 1. So let's go ahead and calculate that. So I am going to get, so inside the parentheses, I got 1.026, and I'm going to raise that to the 4th, and then I'm going to subtract 1. So what I get is that the effective rate, again, remember the effective rate should be a little higher because the simple interest doesn't work as well. So when we did compound interest, in order for a simple interest to match it, it has to be a higher rate. So this comes out to 0.108 or 10.8%. Okay, so we're going to apply now the same thing on the second fund. So the effective rate of the second fund is 1 plus the 10.6% is 0.106. Now we're going to divide that by 2. We're going to square the whole thing, right? Because remember, we're going to put the number of conversion periods as the exponent. So that's just pulling this 2 down here. I just don't want anyone to be like, why are you squaring it? It's because that M happens to be 2 in this problem. Okay, minus 1. All right, so let's go ahead and calculate that. So 0.106 divided by 2 is 0.053 plus 1. And then I'm going to square that. And then I subtract 1. And I get 0.109 if I round. So this is 10.9%. So it's not much of a difference, but it does appear that the Acme fund is better. So Acme is better. Now, why did I say that? Just in case you missed it, 10.9 is bigger than the 10.8, right? 10.9 is a little bigger, not much. So Acme, which was the number 2 option, is the better choice. Okay, so let's go back and see what the next question is. All right, so this is question 8. It's the last question. It's a 0 coupon bonds. Now, I have to tell you, I don't know that much about 0 coupon bonds, but let's just go ahead and see what the problem tells us to do. Okay. Juan is contemplating buying a 0 coupon bond that matures in 10 years and has a face value of 10,000. If the bond yields a return of 5.25 per year compounded annually, how much should Juan pay for the bond? So the 0 coupon bonds just gives you an amount back. So um, so by the face value, it means that he's going to get 10,000. Okay, and then we have a time of 10 years, and we have a rate of return, which is, excuse me, the interest rate is 5.25%, or 0.0525 if we write it as a decimal, and it's compounded annually. So our M equals 1. And so the question is, how much should Juan pay for the bond? So really what this is asking, when you think about what he would be paying for it, you're talking about your initial amount you're putting in, right? So it's actually asking for the principal. So let's go ahead and calculate this. So 10,000 is going to equal P times 1 plus I, and remember I here is going to be the 0.0525 divided by 1. So it's just 0.0525. And we're going to raise it to the n, and n is m, which is 1, times time, which is 10 years, or just 10. So I raise this to the 10. Okay, so we're just going to multiply this out on the right, and I'm going to make my screen bigger. Sorry about that. There we go. So here's my I, 0.0525 divided by 1, because this is being compounded annually. And my N was 1 times 10, or 10. And then I just plugged into the compound interest formula everything that I was given. I was told it was 10,000. And now you could use the present value formula, which is actually just exactly this calculated already for you as a formula, but you don't need to do that. You can just plug into this and just do the algebra. That's really the right, I don't know, it's the same thing. So, okay, let's go ahead and do this. So we're gonna multiply this out. So let me go ahead and say it's 1.1 plus 0.0525 raised to the 10th power. All right, so, and what I'm gonna do is I'm going to divide both sides by that. So this is, and I don't recommend that you round here. So let's just go ahead and write this as 1.0525 to the 10th. So we're gonna do that on both sides. All right, so this is gonna be canceled out on the right, and we're just gonna have that initial amount. So let's go ahead and do the math on the left. So we're going to take 10,000, we're going to divide by this number. and I get that this our initial amount that we want to invest in this, or that Juan should pay for this, is 5,994 and 86 cents. Okay, so there we go. That's the answer to problem number 8. All right. I hope that answers all the questions you might have on this, and I'll see you on Friday. If you have any questions, please reach out to the tutors, or I might have some office hours tomorrow, but hopefully this will help you get these. Once you know these formulas, they're not necessarily really hard to calculate as long as you're putting everything in your calculator correctly. Right. Take care. Bye.